In our last lesson, we focused on finding discontinuities, otherwise known as our horizontal and vertical asymptotes and holes in our graph, based either on the picture of the graph or our function in transformational form. So again, that was where we have some transformations on our parent function of 1 over x, either changing our a value or h value or a k value to predict where that function is going to be. Well, starting with today's lesson, most of our functions are actually going to be in standard form, where we have an expression like ax squared plus bx plus c, both in the numerator and denominator, where we don't necessarily know the transformations just by looking at the function. So to figure them out, what we're actually going to need to do is factor each expression completely, and that will help us determine which discontinuities we have in that function. So again, if you were not completely comfortable with factoring once we finish that unit, please go back and look at Unit 3, especially the 2 trinomial days in there to help review that topic. So looking at finding our discontinuities, there's actually 3 phases that we need to look at, and we want to look at these in order. So the first thing that we always want to do is look for a horizontal asymptote. And the way we determine that is what's the relationship between the 2 polynomial functions, usually trinomials, but not always. What's the relationship between those 2 expressions that we have in the rational function, in our fraction? And so we do this by checking out the degrees. So don't forget, degree of a function is what's the highest exponent you have in that expression. So in our first example, we want to look again, the degree in the numerator, degree in the denominator. So in the numerator, again, if we're looking for the degree, we're looking for the highest exponent on any variables that are in that expression. So we have a 2x, the implied exponent on the x is 1. In our denominator, our degree, our highest exponent on a variable, is a 2. So in this case, our degree in the numerator is less than the degree in the denominator. Now, when this happens, we are always going to have a horizontal asymptote of y equals 0. And again, feel free to verify this, pause the video, go over to Desmos and graph this out, and see if you have an imaginary line at y equals 0, aka your x-axis, that the graph never crosses. Okay, our second case is when our degrees are equal. And so you'll notice in both of these, the highest exponent that we have is the 3. Now, anytime that happens, what we're going to do is we're going to actually look at the leading coefficients. So that would be a good note to put in. So our leading coefficients. In other words, what's that number? What's the coefficient on that term that has the highest degree? And so for this, that means we're going to look at our first leading coefficient in the numerator is a 5, and in the denominator is a 3. And again, don't forget, if you just have an x or x squared or x cubed, what's your leading coefficient then? Just a 1. So keep that in mind when you're looking at those expressions. Okay, and then our third case, well, then our numerator actually has the larger degree. And so in our numerator, for example, 3, we have a degree of 4, again, highest exponent on a variable. Our denominator, our degree is just at 1. When that happens, there is actually going to be no horizontal asymptote. We might have a scenario where we actually have a slanted line as our asymptote. And again, graph this example function out on Desmos and see what happens with it. Now, that being said, slant asymptotes aren't something that we're going to be working with in Algebra 2. Those are something that you might see in Algebra 3 trig and definitely in pre-calculus if you move on to those courses. So keep that in the back of your brain. There still could be an alternate asymptote, just not a horizontal asymptote. So our second step now is algebraically, how can we find the holes in each function? So to do this, we're going to go ahead and factor out both the numerator and denominator of our expression, check to see which factors repeat both in the numerator and denominator. So these would usually be the expressions that we would cancel out if we were simplifying out this expression. And so we would still need to know where that hole is going to be so we know exactly where it is on the graph. So after you've simplified that expression, that x value that came from the factor that you simplified out, plug that into your function to figure out where that point actually doesn't exist on the graph. So let's look at our first example. So our function is x squared plus 4x plus 4 over x minus 5x minus 14. So our first thing we want to do is factor this out. Again, both of these have a leading coefficient of 1, so pretty straightforward factoring. We know we have to have an x and an x. And 4, we can do positive 2 and positive 2, which will get us to that middle term of 4x. Our denominator, again, no leading coefficient, so we both have x's there. 14, we could do 2 times 7. To make that a negative 14, one has to be positive, one has to be negative. And to make the negative 5, we would have a positive 2 and a negative 7. So you'll notice here, I can do 2 possible things with this now. So first off, I can find my horizontal asymptotes. Because I had the same exact degree numerator and denominator, the squareds, or I have 2 factors in the top, 2 factors in the bottom, I know my horizontal asymptote is going to be just dividing the leading coefficients. Because both of those were 1, I know that my horizontal asymptote is 1. So then the second thing I have to do is find the holes. And so for the holes, I'm looking at where are my common factors. So I have a repeated x plus 2 in the numerator and denominator. So that means my hole is going to occur with that factor. Now, just like we found our x-intercepts when we were doing quadratics, we're just going to take that factor and we're going to set it equal to 0 and solve out for x. So x equals negative 2. So we have a hole at x equals negative 2, but we still want to figure out where the point is going to be at that location. So thinking about the fact that I had an x plus 2 factor numerator and denominator, if I simplified those out, then I would be left with f of x equals x plus 2 over x minus 7. So if I plug in my x value that I found for my hole, the number that spits back out, the f of x, our y value, will be our y value on that coordinate. So plugging that in, I have a negative 2 plus 2 in the numerator and a negative 2 minus 7 in the denominator. Well, our numerator comes out to 7, or excuse me, to 0. We knew that was going to happen anyways because I had the x plus 2. And in my new denominator, I have a negative 9, but 0 divided by anything is just 0. So that means our hole is actually going to have the coordinates negative 2, 0. And again, I encourage you to go graph this on Desmos. The kicker is with Desmos, though, it's not actually going to plot that point. But if you try hovering exactly over where x is equal to negative 2, Desmos will eventually tell you negative 2 and then undefined for the y coordinate because you have a hole at that location. So again, feel free to pause the video and try that out. Okay, example 2. We're going to do the same thing. So first, let's find the horizontal asymptote, and then let's find the hole. Okay, so horizontal asymptote, again, I'm noticing my degrees are exactly the same. So my horizontal asymptote on this one, it's going to be another y equals 1 because my leading coefficients are just 1s. Okay, then we look for the hole. So to do that, we need to factor. And actually, I didn't need to turn that back there. Okay, so factoring the numerator, we're going to get an x plus 1, x plus 2 and x plus 3. Again, factors of 6 are 2 and 3, but they add to make that middle term of 5. X squared minus 9, he's one of our patterns. That one is an x minus 3 and x plus 3, difference of squares. And so there's our matching factor. So I know I'm going to have a hole at x equals negative 3. So now I need to find where that hole physically would be on the graph. So simplifying out our factors that matched up, we're left with an x plus 2 over x minus 3. Plug in that negative 3. So negative 3 plus 2 in the numerator, negative 3 minus 3 in the denominator. We're looking at positive, -1 over a -6, otherwise known as 1/6. So our hole would actually occur at the point -3, 1/6. And again, you can find that on a Desmos graph by hovering exactly over where x equals -3, but it will not actually plot a hole at that location. Any of the graphs that I've given you, I've had to physically plot that point to make sure it shows up on the graphic. Alrighty, so that's step 2. So horizontal asymptotes comparing your degrees, holes comparing your factors that match up. And so the last piece that we would look for would be our vertical asymptotes. So vertical asymptotes are going to occur with any of the leftover factors that we have in the denominator. So that's why we need to do the other two things first. We want to do horizontal asymptotes before we lose track of what our degrees are. Then we want to do holes to see, well, which things are matching. And then vertical asymptotes are any of the factors left over that we didn't simplify out. Alrighty, example 6. So again, as always, compare your degrees. The degree in the denominator is bigger than the one in the numerator. So that means this does not have, if it has the larger degree in the denominator, that means our horizontal asymptote is going to be y equals 0. Okay. We don't actually need to worry about holes in this one because we don't have an expression in the numerator. So even when we factor it out, we won't have a matching factor numerator and denominator. I still need to factor it out though, because I need to look for my vertical asymptotes. So factoring out that denominator, I have an x minus 5 and an x plus 4. Again, those will give me that -20 when I multiply, the -1x in the middle when I add. And so each factor that's left in the denominator, you're going to use that as a vertical, or to give you your vertical asymptote. So for your vertical asymptotes, one will occur where x equals 5. So it will not cross that vertical line at x equals 5. And the other at x equals -4. It is absolutely possible to have 2 vertical asymptotes on a graph. We won't see too many of them, but algebraically, that's something that can definitely pop up on a regular basis. Okay, example 7. Again, start with your degrees. So again, the degree in the denominator is bigger on this one. So our horizontal asymptote is going to be y equals 0. Okay, let's go ahead and factor these and see if we have any holes. So we have the numerator is already factored. Denominator is another difference of squares. So we have x plus 9, x plus 7 and x minus 7. And there's our matching factor with the x minus 7. So that means we're going to have a hole at x minus 7 equals 0. Solve that for the x. But again, I need to figure out, well, if I simplify that out, what's going to be left that I could actually use to find the location of that hole. So f of x equals 1 over x plus 7. Plug in that 7. 1 over 14. So the point is actually at 7, 1 over 14. And then our last piece is to look for our vertical asymptote. So any of the factors left over after we simplify. So if we simplified out that the x minus 7, we still have left the x plus 7. So vertical asymptote, set that leftover factor equal to 0. And there's our vertical asymptote. Last piece of this. So this isn't finding discontinuities, but it can absolutely help us when we're finding individual points. And that's finding our x and y-intercepts. So keep in mind, when you have an x-intercept, that's going to be on the x-axis, your y value will equal 0. When you're looking for a y-intercept, the x coordinate will be 0. So in our last 2 examples, let's go ahead and sketch our graphs out and find all of our discontinuities. So we're going to use the rules that we looked at already. We're going to find our x and y-intercepts and sketch out the graph. Alrighty, so example 8. So my degree in the numerator is larger. That means there's no horizontal asymptote. Okay, so now I need to factor. And actually, let's go to a darker color. So x plus 5 and x minus 2 for my factors. That means I do have a matching factor on this one. I have the x plus 5. So my possible hole occurs x plus 5 equals 0, so x equals -5. Plug that into the whatever's left over in the function after you simplify that out. So that means f of -5. We're going to plug that into the x minus 2 that was left in the numerator, but that was it. That's all that's left. So that's -7. So my hole is actually going to happen at -5, -7. Now, we've used everything. Our third thing to look at would be our vertical asymptote, which would be any leftover factors in the denominator, but we don't have any. So we're done with that piece. There's no vertical asymptote either. So no vertical asymptote. And in fact, if I look at what's left over, my function, once I've simplified everything out, looks like x minus 2. Excuse me, let me put the equals in there. Now, that's just a line. So that's a line with a slope of 1 and a y-intercept of -2. So actually, I can graph this first and then find my x and y-intercepts pretty easily on this one. So I know I'm going to have the y-intercept of -2. Let me flip over to red so it pops better on the graph. Slope of 1, so that means I'm just going up 1 over 1 for each point. Except for when I get to -5, -7, there's going to be a hole in the graph. And that is our function. So even just sketching this out because it was a line, I also know my x-intercept is at the point 1, 0, and my y-intercept is at the point 0, -1. Alrighty, last example. So this one does have a rational expression. I can factor the numerator and denominator completely. So here we go. Okay, first off though, before I do that, I'm noticing my degree in the numerator and denominator is exactly the same. So I need to look at my coefficients for my horizontal asymptote. Well, my coefficient on the denominator is just a 1. So that means my horizontal asymptote is going to be y equals 2 over 1, otherwise known as 2. Okay, now factor out your expression. I can factor 2 out of the numerator. And then I can still keep factoring because that's the difference of squares. So I have a 2, an x plus 1, and an x minus 1. In the denominator, I just have an x plus 2 and an x minus 2. So because even though we have that 2 in the numerator that we factored out our GCF from that expression, I do not have any matching factors. So this is a scenario where we have no hole in the graph, so no missing points in the graph. But I do have 2 vertical asymptotes. One is going to happen where we have x plus 2, otherwise known as x equals -2. And the other is going to happen at x minus 2 equals 0, aka where x equals +2. So I can actually sketch this out almost to begin with. I have a horizontal asymptote at y equals 2, and then vertical asymptotes at -2 and +2. Now this graph is going to look a little weird, so I do want to go ahead and find my x and y-intercepts with, well, to give me an idea of where the pieces of this graph are going to go. So for x and y-intercepts, again, my x-intercept means my y equals 0. So my y, my f of x, so 0 equals, well, wait a second. The only way for a fraction to equal 0 is if the numerator equals 0. And so that means that 2x squared minus 2, our original problem, would equal 0. And it's a lot easier for me to solve for x from this format. So add a 2 to both sides. divide both sides by 2, and I actually get a really nice number on this one. X squared equals 1, otherwise known as x equals 1, square root of 1. Now, we're not going to have, well, possibly, let's check to see what happens on this one. So because when we take the square root of 1, technically we have a plus minus. So we should have one y-intercept at positive 1 and one, or excuse me, x-intercept at negative 1. And so now let's look for our y-intercept. So y-intercept, so that means x equals 0. So plug your x equals 0 into your function. I'm going to go ahead and write to my original function just in case I didn't factor it properly. So f of 0 would be 2 times 0 squared minus 2 and 0 squared minus 4. Well, that cancels out the first two terms. So we have a -2 over -4, otherwise known as a positive 1/2 is going to be my y-intercept. So positive 1/2. So wait a second, it looks like I'm almost starting to graph a parabola. And in fact, if I sketch this out, I'm going to have one piece of my graph here that's kind of bordered by those asymptotes. And if I want to follow what we've seen with the previous functions, that means my other branches are going to be one at the top right and one at the top left. And again, if you don't believe me, go ahead, graph this in Desmos and see what happens. Okay, as always, let me know if you have any questions. Otherwise, start checking out your practice.